Hello and welcome to the Sleepy Science. I am happy to see you here. Tonight we discuss how galaxies are born.
So, before starting, please tell us in the comment section where are you from and what's the current time in your country when you watch this video. Let's start without wasting your time.
Close your eyes and drift into the quiet of the cosmos. Tonight, we journey far beyond the stars, into the ancient darkness where the first galaxies were born. From clouds of gas and whispers of gravity, entire island universes began to spin. Let's float gently through time and uncover the peaceful mystery of how galaxies, like our own Milky Way, came to life. First, the cosmic cradle. You float in the dark, before time has shape. Here, in the silence between stars, the first whispers of matter stir, a delicate dance of dust and gravity, gathering like breath before a sigh. The universe is young, and so are you. Imagine a darkness so complete it isn't merely the absence of light, but the absence of absence itself. This is where you begin, suspended in a void that hasn't yet learned to be empty. There are no reference points here, no horizons or edges. Just an infinite potential, waiting. The universe hasn't decided what it wants to be when it grows up. All possibilities exist simultaneously in this quantum soup of maybes. Time hasn't yet begun its relentless march forward. What you perceive as moments stretch and yawn like a cat in sunlight, each second lingering for eternity before dissolving into the next. There is no before or after here, just an endless now where everything that ever will be already exists in seedling form. The particles that will one day become your fingernails, your breath, your memories, are here already, though they don't know it yet. They dance to a music so quiet even silence strains to hear it. Gravity awakens first. Not the gravity you know from dropped apples or falling leaves, but something more fundamental, the universe's first acknowledgement that things might want to be together rather than apart. It begins as the faintest inclination, a whisper of attraction between particles that barely exist. Some regions contain slightly more potential than others. These microscopic wrinkles in space-time will become the seeds of galaxies, though it will be billions of years before anyone calls them that. The hydrogen atoms, though they aren't properly atoms yet either, begin a slow waltz. They move with glacial patience, drawn together by forces they can't comprehend. There's no rush here at the beginning of everything. Each particle has all the time in the world to find its place. They cluster in groups of thousands, then millions, then billions, each addition making the gravitational pull slightly stronger, the dance slightly faster. You watch as these molecular clouds begin to take shape. They're not yet stars or planets, just vast, diffuse gatherings of gas so thin that Earth's best vacuum would seem crowded by comparison. But density is relative, and in the emptiness of the early universe, these clouds might as well be mountains. They ripple and sway, their edges blurring into the surrounding void. Occasionally, two clouds will brush against each other in slow motion, their molecules exchanging shy greetings before continuing on their way. Deep in the heart of the largest cloud, something remarkable is happening. The hydrogen atoms are being pressed closer together than they'd like. Their electrons protest this invasion of personal space, creating a subtle pressure that pushes back against gravity's insistence. For eons, this standoff continues, collapse versus resistance, gravity versus quantum mechanics. The cloud shudders with this internal debate, its form shifting like a restless sleeper. Then comes the moment of surrender. Some critical threshold is crossed, some unspoken agreement reached between the forces of nature. The center of the cloud begins to compact in earnest now. Hydrogen atoms fuse together in pairs, then fours, then eights. Each fusion releases a tiny packet of energy, not yet enough to call it light, but enough to warm the surrounding gas. The process accelerates as the core grows denser, hotter. What began as a reluctant compaction becomes an enthusiastic collapse. The first photons emerge hesitantly, as if unsure of their welcome in this dark universe. They're not the brilliant starlight we know today, but softer, more diffused, the cosmic equivalent of a child's nightlight. They bounce between gas particles, slowly working their way outward from the growing core. Each interaction transfers a bit of energy, heating the surrounding material further. The entire cloud begins to glow with a faint, pearlescent light. As you watch, the structure becomes more organized. The random motions of gas particles give way to a slow, stately rotation. The cloud flattens into a disk, its outer edges cooler and calmer than the turbulent core. Wisps of material spiral inward like water draining from a bathtub, feeding the growing protostar at the center. The birth of a star is never a single event, but a process that unfolds over millennia, a gradual awakening rather than a sudden explosion into being. The universe holds its breath as the core temperature passes 10 million degrees. Hydrogen fusion begins in earnest now. No longer tentative experimental reactions, but the sustained nuclear fire that will burn for billions of years. The first true star flickers to life, its light pushing back against the darkness that has reigned since the beginning. It's not alone for long. Across the young universe, other clouds reach their own moments of criticality. Points of light emerge like candles being lit one by one in a vast cathedral. You float among these firstborn stars, watching as they begin the work of element building. The hydrogen and helium that made up the primordial universe are being transformed in their cores, fused into heavier elements that will one day form planets, oceans, and living creatures. But that story belongs to another chapter. For now, there is only this quiet miracle: the universe has learned. And as you watch these first stars blink into existence, you realize something profound. The atoms that currently make up your body will one day return to this cosmic dance. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in stellar furnaces like these. You are, quite literally, made of stardust. The universe remembers its beginnings, and so do you, in some deep, cellular way. The darkness is no longer absolute. It's been broken by these first brave points of light, these cosmic pioneers. They don't know it yet, but their lives will be short and brilliant. They will burn fast and die young, seeding the universe with the heavy elements that make our existence possible. Their deaths will be spectacular, supernovae that outshine entire galaxies, but that's a story for another night. For now, there is only this quiet moment of creation, this cosmic dawn. The universe has taken its first trembling steps toward complexity. And you, whether as observer or participant, are here to witness it all. The newborn stars pulse gently in the dark, their nuclear hearts beating in slow unison. Already, their light begins to sculpt the surrounding gas into shapes that will one day become home. Second, the first light. A glow emerges, timid and golden, as atoms learn to embrace. Hydrogen hums its ancient song, and photons, newborn and restless, begin their endless journey. You watch as darkness lifts its veil. The universe exhales. Where before there was only formless potential, now there is structure, fragile, trembling structure, but structure nonetheless. Those first protostars you witnessed birthing themselves from the void have grown restless in their nuclear cradles. Their cores, once cool and uncertain, now hum with a terrible, beautiful intensity. The darkness that reigned supreme for eons finds itself challenged for the first time. You float closer to one of these newborn suns, though newborn hardly captures the millennia of slow, deliberate collapse that brought it here. Its surface ripples with plasma currents, still settling into the rhythms it will maintain for millions of years. The light it emits isn't the clear white-yellow of mature stars, but a tentative orange-gold, as if the star itself is unsure of its own brilliance. Photons that began their journey in the star's core now reach its surface and leap into space, the first true starlight the universe has ever known. These photons have an extraordinary journey ahead. Some will travel for billions of years, crossing distances so vast they defy comprehension. Others will meet gas atoms almost immediately, being absorbed and re-emitted in an endless game of cosmic tag. You watch as the light pushes against the surrounding hydrogen clouds, gently ionizing the gas, teaching atoms how to interact with radiation. It's a slow education. The universe is still overwhelmingly dark, but the principle has been established. Light exists. Darkness will never again be absolute. The star's golden glow reveals something remarkable about its surroundings. What appeared as formless void now shows delicate structure, tendrils of gas illuminated from within, like fog caught in a street lamp's beam. These are the star's siblings, other protostars in various stages of formation. Some are still dark cocoons of gas, barely begun their gravitational collapse. Others show the first flickers of fusion deep within their cores. A few have already achieved full stellar consciousness, their light joining the chorus pushing back against the cosmic night. You notice something peculiar about these first stars. They're massive, far larger than most stars that will form in later epochs. Without heavier elements to help them radiate away heat during formation, they grew to tremendous sizes, some containing hundreds of times the mass of our sun. This gives them a terrible beauty, but also seal their fate. The very processes that make them so brilliant will cause them to burn out. Their lives measured in mere millions of years rather than billions. Deep in the star's core, the alchemy of creation continues unabated. Hydrogen nuclei fuse into helium, releasing energy with every atomic marriage. But this is no simple process. It's a quantum dance of unimaginable complexity. Protons, which normally repel each other fiercely, occasionally tunnel through their mutual electromagnetic barriers in rare, statistically improbable events. The star's enormous gravity and temperature make these unlikely events commonplace. But still, every photon born in this core represents a minor miracle of physics. The star's outer layers tell another story. Convection currents the size of solar systems carry heat from the interior to the surface in great, rolling waves. Magnetic fields twist and snap, creating enormous prominences that arc hundreds of thousands of kilometers into space. Occasionally, these magnetic disturbances release bursts of radiation that ripple through the surrounding gas clouds, triggering new rounds of star formation in distant nurseries. You become aware of the star's voice, not sound in the conventional sense. Sound needs molecules to travel through, and space is still nearly empty, but rather the steady pulse of its electromagnetic emissions. It sings across all wavelengths, from radio whispers to ultraviolet shouts. This symphony contains coded information about the star's composition, age, and future, a message any sufficiently advanced civilization could one day decode. As you watch, the star's radiation begins sculpting its birth cloud into fantastic shapes. The nearby gas, heated by the starlight, starts to evaporate, creating a glowing bubble around the newborn sun. Farther out, the radiation pressure pushes dust grains into alignment, causing them to polarize the starlight in beautiful, intricate patterns. The universe is learning how to interact with light, and light is learning how to shape the universe. A thought occurs to you: these first stars have no planets. The universe hasn't yet manufactured the heavier elements needed to form rocky worlds. Any civilizations that might one day arise will have to wait for generations of stars to live and die, scattering their enriched ashes across the cosmos. For now, these brilliant pioneers shine alone, their light unappreciated by any eyes. Yet their importance cannot be overstated. Every element in your body heavier than hydrogen, the oxygen you breathe, the carbon that forms your cells, the iron in your blood, will one day be forged in stars like these or their descendants. The calcium in your bones was once the outer layers of a dying star. The phosphorus in your DNA may have formed in the violent death throes of one of these very first massive stars. The light grows stronger now as more stars awaken across the young universe. What began as isolated points of gold and an endless black now starts to resemble a sparse network, a cosmic web of illumination. The darkness between stars remains profound, but it's no longer invincible. Photons crisscross the expanding universe, their paths occasionally intersecting with gas clouds, sometimes traveling unimpeded for billions of years. You notice something curious happening at the boundaries where starlight meets primordial gas. The ultraviolet radiation from the hottest stars is powerful enough to strip electrons from hydrogen atoms, creating vast ionized regions around each luminous beacon. These bubbles of plasma will be the birthplaces of future complexity, where chemistry will one day give rise to molecules, and molecules to life. The universe is changing before your eyes, not in human timescales, but in the slow, inevitable progression of cosmic evolution. The first stars have begun the work of transforming the simple, uniform early universe into the complex, structured cosmos we know today. Their light carries both energy and information, shaping everything it touches. As you prepare to drift onward, you realize this light will never stop traveling. Some of these photons will still be crossing intergalactic space when the last stars in the universe wink out trillions of years from now. They'll carry the memory of these first luminous moments to the very edge of eternity. The light has only just begun its journey, and already the darkness will never be the same. As you turn your attention to the spaces between the stars, you sense gravity gathering its strength, preparing to weave these scattered points of light into something greater. Third, threads of gravity. Invisible hands pull at the fabric of space, weaving strands of gas into delicate filaments. You drift through these rivers of potential, where gravity writes its first love letters to the void. The universe has awakened from its dark slumber, but its eyes are still half closed. Those first brave stars now float like distant campfires in an endless forest, their light barely touching the spaces between them. Yet something profound stirs in those shadows, an invisible architecture beginning to take shape. You feel it before you see it, the faintest tug, the gentlest suggestion of direction in what was once perfect emptiness. Gravity, the shyest of fundamental forces, has been at work this whole time. While light announced itself with golden fanfare, gravity has been weaving in silence, patiently drawing matter together with infinite care. Its work is visible now in the subtle patterns forming between the stars. What appeared as random scatterings of luminous points now reveals hidden connections, delicate threads of gas and dark matter stretching across the void like spider silk glistening with morning dew. You drift toward one of these primordial filaments, watching as hydrogen atoms slide along its length like beads on a cosmic abacus. The structure isn't solid, it's more a river of probability, a highway where atoms are slightly more likely to be than anywhere else. The filament stretches for hundreds of thousands of light years, yet is only a few hundred light years across, a shimmering bridge between two growing clusters of stars. Its gravity is too weak to pull you in, but strong enough to shape the paths of passing gas clouds, herding them toward the denser regions at either end. The scale is difficult to comprehend. These filaments form a web spanning the entire observable universe, with galaxies eventually growing at the intersections like dewdrops on a spider's web. But right now, in these early epochs, the web is still being spun. Most intersections contain only the faintest glow of protogalaxies, collections of stars too sparse to be called true galaxies yet. As you follow the filament's curve, you notice dark matter flowing through it like an invisible current. Though it neither emits nor reflects light, its presence can be felt through its gravitational influence. The ordinary hydrogen gas moves in harmony with this unseen partner, the two components weaving together in an intricate dance. Dark matter's gravity provides the scaffolding, while normal matter follows, cooling and collapsing into stars along the densest pathways. The temperature variations are extraordinary. In the filament's heart, the gas is relatively warm, perhaps a few thousand degrees, heated by the first starlight and by collisions between atoms. But in the slightly denser regions, where gas has begun to pool, miraculous cooling occurs. Hydrogen molecules, H2, formed when two atoms tentatively link hands, vibrate and rotate, radiating away heat. This allows the gas to condense further, creating the seeds for future galaxies. You notice something curious happening at one of the filament's nodes. The gas there has become turbulent, swirling in complex patterns as competing gravitational pulls stretch and compress it. Shock waves from nearby supernovae, the dramatic deaths of those first massive stars, ripple through the structure, triggering new star formation. Heavy elements forged in stellar cores now mix with the pristine hydrogen, enriching the cosmic brew. These metals, as astronomers call all elements heavier than helium, will allow future stars to form more efficiently, with planets around them. The filament itself is changing. What began as a nearly straight line now develops kinks and twists as gravity amplifies tiny initial irregularities. Sections begin to contract, their self-gravity overcoming the expansion of space itself. The structure is becoming self-aware in a gravitational sense, realizing it can collapse inward rather than simply stretch with the expanding universe. You watch as one particularly dense knot begins to separate from the cosmic web. It contains perhaps 1,000,000 times the mass of our sun in gas, plus several times that in dark matter. The gas cools further, fragmenting into clumps that will become star clusters. Rotation becomes important now. As the cloud contracts, it spins faster, flattening into a disk. The beginnings of a spiral galaxy are taking shape before your eyes, though it will be hundreds of millions of years before it resembles anything like the Milky Way. Dark matter continues to play its mysterious role. While normal gas can radiate away energy and collapse, dark matter particles simply pass through each other, unable to cool. They form an enormous, diffuse halo around the developing galaxy, its gravity shaping the overall structure while the gas does the interesting work of making stars and planets. The filament isn't alone. Looking around, you see similar structures stretching in all directions, some nearly parallel to yours, others intersecting at various angles. Together, they form a three-dimensional lattice, with voids between them that will grow emptier as matter continues flowing into the web. Already, some filaments are beginning to merge where they cross, creating more massive rivers of gas feeding growing protoclusters of galaxies. Time accelerates as you watch. What began as tiny density fluctuations in the early universe has grown into an intricate cosmic tapestry. The largest filaments now contain multiple protogalaxies strung along their lengths like pearls. Gravity's patient work is becoming visible. Where matter was once nearly uniform, now there is structure, hierarchy, the beginnings of cosmic geography. Yet the universe remains profoundly alien by modern standards. There are no grand spiral galaxies yet, no elliptical galaxies, no quasars. The stars that exist are strange beasts, massive, blue-hot, and short-lived compared to the sun. The chemistry is simple, mostly hydrogen and helium with traces of lithium. No planets could form in such an environment, no life as we know it. You sense something building, though. The same gravitational forces that shape these filaments continue working on larger scales. Entire superclusters of galaxies are being outlined in the cosmic web, though their full glory won't be revealed for billions of years. The great walls and voids of the large-scale universe are already present in embryo form, their patterns determined by quantum fluctuations in the universe's first moments. As you prepare to move on, you notice one last wonder. Two nearby filaments are beginning to dance around each other, their mutual gravity causing them to spiral slowly together. In time, they'll merge completely, their gas feeding a growing cluster of young galaxies. The process is achingly slow by human standards, but inevitable in gravitational terms. The universe is growing up. What began as a nearly smooth distribution of matter has developed texture, variation, personality. Gravity's handwriting is becoming legible in the cosmic book of creation. As the filaments tighten their gravitational embrace, their intersecting nodes grow luminous with stellar fire. What began as whispers in the dark now becomes a chorus. The first true galaxies are learning how to sing. Fourth, nurseries of stars. Clouds collapse and sparks ignite. Here, in these velvet pockets of chaos, stars are born, each one a flickering promise against the infinite. You count their pulses like a lullaby. The cosmic web has done its work. Where once there was only formless gas, now great rivers of matter flow along invisible filaments, pooling where gravity whispers loudest. You find yourself drifting toward one such gathering, a vast molecular cloud, its edges frayed by stellar winds, its heart pregnant with possibility. This is no ordinary cloud. It contains enough material to craft 10,000 suns, and it hums with the vibrations of its own slow-motion collapse. The cloud welcomes you into its embrace, its density increasing gradually as you sink deeper. At first, the hydrogen molecules are so sparse that kilometers separate them, a vacuum by earthly standards. Yet compared to the intergalactic void outside, this is already a crowded metropolis. The temperature hovers just above absolute zero, allowing complex organic molecules to form on flecks of dust, carbon monoxide, water ice, even simple sugars. These microscopic grains will become the building blocks of solar systems, though that future is still ages away. As you penetrate further, the gas grows thicker. Light from nearby stars filters through in muted tones, reddened and dimmed by passing through so much material. The cloud's outer layers are turbulent, stirred by shock waves from distant supernovae and the gravitational pull of passing stars. This chaos creates pockets of higher density, knots where gravity gains the upper hand over pressure, where the balance tips irrevocably toward collapse. One such knot draws your attention. A few dozen light-years across, it contains several hundred solar masses of gas. The core is dark, shielded from outside light by its own outer layers. Here, in this isolated pocket of the universe, something remarkable is about to happen. The gas has begun to contract, slowly at first, then with increasing urgency as its self-gravity grows stronger. The physics is elegant in its inevitability. As the cloud contracts, potential energy converts to heat. Molecules move faster, colliding more frequently. The temperature rises from 10 Kelvin to 20, then 50. At these low temperatures, even modest heating significantly affects the gas's behavior. The increased thermal pressure fights against gravity's pull, creating a delicate balance that determines the cloud's fate. Then comes the moment of decision. A particularly dense region at the cloud's heart reaches a critical threshold. The gas can no longer support itself against its own weight. With a slowness that belies the violence of the process, the core begins to collapse in earnest. You watch as the central region separates into fragments, each destined to become its own star. The largest fragment, containing perhaps twice the mass of our Sun, collapses fastest. As it shrinks, its rotation increases, a cosmic figure skater pulling in her arms to spin faster. The gas flattens into a disk, its outer regions continuing to spiral inward while the core grows ever denser. At the center, temperatures now reach thousands of degrees. Hydrogen molecules dissociate into atoms, then ionize into plasma. The pressure is tremendous, yet gravity's grip is stronger still. The protostar continues to shrink, its surface glowing a dull red as it radiates away the energy of its collapse. Above and below the growing star, bipolar jets erupt, twin fountains of material shooting outward at nearly the speed of light. These jets are the star's birth cry, a necessary release of angular momentum that allows the central object to continue contracting. They extend for light years, eventually plowing into the surrounding molecular cloud and creating glowing shock fronts. The protostar is not alone. Throughout the cloud, dozens of similar collapses are underway. Some produce single stars, others create tight-knit groups that will remain gravitationally bound for billions of years. The most massive collapses proceed fastest, their enormous gravity overcoming all resistance. These will become the brilliant blue stars that dominate a young cluster's light. The stellar nursery is alive with motion. Newborn stars jostle for position, their gravitational interactions flinging some outward while drawing others closer together. Gas swirls in complex patterns, funneled by magnetic fields and sculpted by stellar radiation. Dark lanes of dust weave through the glowing gas, creating shadowy fingerprints against the luminous background. You notice something peculiar about the most massive protostars. They reach the main sequence, the stable hydrogen-burning phase, while still accreting material. Their radiation is so intense that it begins to evaporate their own birth clouds, creating glowing cavities around them. These are the stars that will live fast and die young. They're spectacular supernova deaths destined to seed the galaxy with heavy elements. Meanwhile, the smaller stars take their time. A solar mass protostar might spend 100,000 years in collapse before beginning hydrogen fusion. Even then, it continues to gather material from its surrounding disk for millions of years. Some of this material will form planets, though in this early epoch, the necessary heavier elements are still scarce. The stellar nursery evolves before your eyes. The first massive stars to form have already begun influencing their environment. Their ultraviolet radiation ionizes surrounding gas, creating glowing HI regions. Their stellar winds carve bubbles in the molecular cloud, compressing nearby regions and triggering new rounds of star formation. It's a delicate balance. Too much radiation too quickly can disrupt star formation altogether, blowing away the natal cloud before smaller stars have time to form. But in this particular nursery, the process proceeds at a measured pace. Multiple generations of stars take shape, the massive blue ones first, followed by smaller yellow and red stars as you focus on one average-sized protostar, not unlike our Sun in its infancy. Its accretion disk shows intriguing structure, spiral density waves, and possible gaps where protoplanets may be forming. The chemistry here is complex, with water and organic molecules frozen onto dust grains in the disk's cooler outer regions. Given time, these ingredients will become comets, asteroids, and perhaps even the building blocks of life. Fifth, collisions in slow motion. Giants meet, not with violence, but with a patient entanglement. Their stars pass like shy strangers, merging halos of light. You marvel at how destruction can be so gentle. The universe has grown older. Where once there were only isolated points of light, now great cities of stars drift through the dark, galaxies taking their first tentative shapes. You find yourself drawn toward two such spirals, their outlines still soft at the edges, their spiral arms not yet fully formed. They move toward each other with a slowness that makes continental drift seem hasty. At this pace, their dance will take hundreds of millions of years to complete, yet already their mutual gravity begins to sculpt their futures. The first thing you notice is how much space there really is. Galaxies look dense in illustrations, all tightly packed stars and glowing gas. But the reality is profoundly empty. If stars were grains of sand, each would be kilometers apart. When galaxies collide, it is less a crash of solid objects and more a gradual rearrangement of sparse fireflies in a vast darkroom. Yet for all this emptiness, the interaction is real. The galaxy's outer halos, tenuous spheres of dark matter and stray stars, have already begun to overlap. You watch as invisible gravitational fingers pluck at both systems, distorting their perfect spirals into something new. The first visible sign comes in the form of delicate bridges of stars, drawn out like taffy between the two approaching giants. These are the galaxy's outermost inhabitants feeling the tug of a new master long before their inner cousins will notice anything amiss. As the galaxies draw nearer, their disks begin to respond. Spiral arms, once neatly wound, now stretch and warp. The thinner gas clouds oscillate like disturbed water, sending ripples through both systems. Some regions compress under these gravitational tides, triggering bursts of new star formation. Young blue star clusters appear like strings of pearls along the distorted arms, the galaxy's instinctive response to the coming merger. The real magic happens in the gas clouds. While stars themselves rarely collide, the distances between them remain vast even during a merger. The diffuse hydrogen between stars has no such protection. Great waves of gas crash together, their collisions creating shock fronts that glow in X-rays. In these violent meetings, new elements are forged, not through nuclear fusion, but through sheer kinetic energy transforming into heat and light. The galaxy's interstellar mediums are becoming one long before their stellar populations will mix. You notice something curious happening to the galaxy's central black holes. Both were quiet, well-fed monsters before the encounter, content to slowly accrete whatever matter came too close. Now, as their host galaxies interact, streams of gas are funneled toward both cores. The black holes begin to feast, growing brighter as they convert stolen matter into energy. In time, billions of years from now, these two behemoths will themselves merge, but for now they simply awaken from their slumber, casting brilliant cones of radiation that illuminate the surrounding chaos. The dance grows more intricate as the galaxies complete their first pass. They don't collide head-on, but rather graze each other in a cosmic near-miss. Yet gravity ensures this is no fleeting encounter. The galaxy's mutual attraction has stolen enough of their kinetic energy to bind them together permanently. They will separate for a time, reaching. During this interlude, the damage becomes apparent. Both galaxies have lost their pristine spiral forms. One now sports a long tidal tail, a river of stars and gas pulled free during the close encounter. The other shows a pronounced warp in its disk, as if some giant hand had twisted it slightly. Yet there's beauty in this distortion. The galaxies are exchanging material, sharing their stellar populations in an act of cosmic cross-pollination. Stars born in one galaxy will spend their twilight years in another. As the galaxies prepare for their second encounter, star formation reaches a crescendo. All through both systems, compressed gas clouds collapse into new stellar nurseries. The merger has created ideal conditions for star birth, turbulence, density waves, and abundant raw material. The galaxies blaze with newborn clusters, their blue-white light overpowering the yellow glow of older stars. This is the starburst phase, when a merging galaxy pair can outshine isolated galaxies of similar mass by an order of magnitude. Yet even amid this fertility, you sense something being lost. The cool, delicate hydrogen so necessary for future star formation is being rapidly converted into stars or blown away entirely by supernova shocks. These galaxies are spinning their gas reserves in one glorious burst of creation. After the merger completes, they'll be left with less material for future generations of stars. The universe is learning that even its most spectacular events come with trade-offs. The final merger proceeds with surprising grace. There are no dramatic explosions, except the routine supernovae of massive stars. Instead, the two galaxies slowly coalesce, their stars finding new orbits in the combined gravitational field. The result isn't immediately recognizable as either original galaxy, nor as any standard galaxy type. It's a messy, luminous thing, all loops and streams of stars with no clear pattern. Given time, hundreds of millions of years more, this chaotic merger remnant will settle into a smooth elliptical galaxy. The violent relaxation process will erase most traces of the original disks, leaving behind a featureless ellipsoid of stars. The gas not used in star formation will either be blown away or settle into a hot, diffuse halo. The brilliant blue star clusters will age into yellow, then red, their massive stars dying off to leave behind cooler, longer-lived siblings. You realize this merger represents both an ending and a beginning. The original galaxies, each with their own history, their own unique stellar populations, are gone forever. Yet their combination has created something new, something that couldn't have existed without this cosmic collision. The chemical enrichment from all the new star formation has created heavier elements that will someday be incorporated into planets. The gravitational stirring has sent some stars careening into the galactic halo, where they may one day host planetary systems in unusual quiet orbits. Most remarkably, the merger has changed the very shape of space in its vicinity. The combined galaxy's gravity now molds the local cosmic web, influencing how nearby gas flows and where future galaxies may form. The ripples from this event will propagate through the structure of the universe for billions of years. As you watch the merger remnant begin to settle, you notice something that gives you pause. Among all the chaos, some stars have been flung entirely free of the new galaxy. These intergalactic wanderers will spend eternity drifting through the void between galaxies, their planetary systems, if they have any, bathed in perpetual night. You wonder about the view from such worlds, a sky nearly empty of nearby stars, just the distant glow of other galaxies stretching away to infinity. The universe continues its slow evolution. Where once there were two distinct spirals, now there is one larger, redder galaxy. Its story has merged with another, creating something greater than part. This is how galaxies grow, not just through steady accretion of gas, but through these occasional grand unifications. Our own Milky Way contains the remnants of such mergers in its halo, and in billions of years it too will merge with Andromeda in a similar slow-motion ballet. As the last ripples of the merger fade, a deeper darkness makes itself known, not the absence of light, but something far more mysterious, its presence felt only in the way stars move just a little faster than they should. Sixth, the dark embrace. Something unseen holds it all together. Dark matter hums beneath the surface, an invisible scaffold for the glittering above. You feel its presence like a shadow behind a candle's flame. The merged galaxy spins before you, its stars tracing lazy arcs through the aftermath of collision. But something is wrong. Not wrong in the sense of broken, but in the way a half-remembered dream feels wrong upon waking. The stars at the galaxy's outer edges move too quickly, their velocities defying the pull of visible matter alone. They should be drifting slower, their orbits decaying as they stray further from the luminous core. Yet they race on as if tugged by unseen hands. You reach out, not with fingers but with perception, and feel it at last, the dark embrace. An ocean of invisible matter cradles the galaxy, its gravity shaping everything from within. This is no mere absence of light. It is something else entirely, a substance that interacts with the universe only through gravity's gentle touch. The stars you see are just froth on this vast, hidden sea, the luminous markers of something far greater moving beneath. Dark matter's presence reveals itself in subtle ways. The galaxy's rotation curve, the graph of orbital speeds at different distances from the center, should fall off at the edges like our solar system's planets do. Instead, it remains stubbornly flat, implying mass where no light shines. Gravitational lensing betrays it too. Distant galaxies appear, warped as their light passes through these unseen halos. Even the cosmic microwave background carries its fingerprint, the slight temperature variations that seeded all structure. You dive deeper into the halo, this sphere of mystery that extends 10 times further than the galaxy's visible edge. Here, dark matter particles, if particles they are, stream through each other like ghosts in the night, feeling only gravity's whisper. They don't collide, don't emit light, don't do anything but be, and in their being, shape the fate of galaxies. The mathematics of their dance is beautiful in its simplicity. Dark matter's gravity drew ordinary matter together after the Big Bang, creating the wells where gas pooled and stars ignited. Without this unseen scaffold, galaxies would have taken far longer to form, perhaps never achieving their grand designs. The cosmic web you witnessed earlier? Its filaments are dark matter's bones, with luminous matter merely dressing the skeleton. Yet for all its dominance, dark matter remains frustratingly aloof. Decades of experiments hunt for it in deep underground labs, hoping to catch the rare interaction with normal matter. So far, the detectors remain silent. Perhaps the particles are too massive, or too weakly interacting. Or perhaps we've been searching for the wrong thing entirely. You notice something peculiar about the merger's aftermath. While the visible galaxies have coalesced into one, their dark matter halos remain partially distinct, like two smoke rings interpenetrating but never fully mixing. This explains why some stars were flung so far during the collision. The complex gravitational field from these overlapping halos created chaotic orbits. The dark matter distribution isn't smooth either. Simulations suggest it should be clumpy, with dense subhalos orbiting within the larger halo. Some of these may host their own dwarf galaxies, visible only by the dim glow of their stars. Others remain completely dark, their presence detect. A thought chills you. Most of the universe's matter is like this. Invisible, untouchable, yet omnipresent. For every proton in your body, there are 5 of these shadow particles surrounding you right now, passing through you as you read this. Your home galaxy swims in a sea of them. Your solar system moves through their currents, and you, right this moment, are being traversed by millions that originated in other galaxies entirely. Yet dark matter isn't entirely alien. Without it, you wouldn't exist. Those first density fluctuations it amplified allowed stars to form early enough that generations could live and die, forging the heavy elements that make up your body. Its gravity shaped the cosmic web that fed growing galaxies. Even now, it holds your galaxy together against the expanding universe's pull. You turn your attention to the larger scale. Dark matter's influence extends far beyond single galaxies. Entire clusters swim in its deeper wells, They're visible gas heated to millions of degrees by the gravitational crush. The great walls and voids of the cosmic web, all traced first in dark matter's distribution before ordinary matter followed. There are competing ideas about its nature. Cold dark matter, slow-moving particles, fits most observations well. But some researchers suggest modifications to gravity itself might explain the phenomena, though these theories struggle with all the evidence. Others propose entire dark sectors, hidden families of particles interacting through their own forces. The truth remains elusive, floating just beyond our grasp like a shape in fog. As you watch, a dwarf galaxy passes through the main halo. Its stars disperse like dandelion seeds in wind, but its dark matter continues on, barely noticing the interaction. This is how some ghost galaxies form, systems so dominated by dark matter that their few stars seem like an afterthought. The merged galaxy's dark halo is settling now, finding a new equilibrium. Its gravity will determine how the visible matter rearranges over billions of years. Already, it's funneling gas toward the center, feeding the now-merged supermassive black hole. The dark matter doesn't care about the light show. It simply continues its endless, silent dance. You realize with some irony that while dark matter outweighs normal matter 5-1, it's the normal matter that does all the interesting things, forming stars, planets, and people. Dark matter is the shy stagehand, never stepping into the spotlight, yet making the performance possible. Your journey through the halo leaves you with more questions than answers. What is this stuff that shapes the cosmos? Will we ever detect it directly, or must we always infer its presence through gravity's subtle hints? And what other invisible actors might be out there, quietly pulling strings we haven't yet noticed? The merged galaxy spins on, its stars tracing paths dictated largely by what we cannot see. The universe, it seems, prefers to keep some secrets. As you pull away from the galaxy's dark embrace, your attention is caught by faint trails of stars, the lingering remains of smaller galaxies torn apart long ago, their sacrifice written in the halo's glow. Seventh, echoes of the first stars. The oldest giants have long faded, but their ashes linger, seeds for new worlds. You sift through their remnants, stardust on your fingertips, and wonder if you, too, are made of their farewells. The merged galaxy's outer halo stretches before you like a vast archaeological dig, layer upon layer of stellar history waiting to be read. Here, far from the brilliant core, the galaxy keeps its oldest memories. Stars move in slow, looping orbits, some tracing paths they've followed for billions of years. Their light is tired, reddened by time. Their composition simple and pure compared to the younger generations nearer the center. You focus on one particular star, an ancient red giant pulsing wearily in the halo. Its light carries a story written. There's almost no iron here, no calcium, no silicon. Just hydrogen, helium, and the faintest whisper of lithium. This is a relic of the first stellar generation, a survivor from when the universe knew only these three elements. Its very atoms remember the cosmic dawn. The star's atmosphere is a window to the past. As you drift closer, its swollen surface reveals strange convection patterns, massive cells of plasma larger than our solar system, slowly churning material from the core upward. This mixing brings traces of the star's internal nuclear history to the surface. There are no heavy elements here because the star was born before the universe knew how to make them. Its composition mirrors that of the primordial gas cloud it formed from, a time capsule floating in the galactic outskirts. But something is odd. The star contains barely any lithium at all, far less than Big Bang nucleosynthesis models predict. The answer lies in its interior. Over billions of years, the lithium has been destroyed in nuclear reactions near the star's core. Even this small deviation from primordial purity tells a story about stellar evolution's relentless chemistry. You turn your attention to the space between these ancient stars. Here floats the dispersed remains of their massive siblings, the true first generation. Those stars, hundreds of times more massive than our sun, lived fast and died violently within a few million years. Their supernovae were different from anything seen today, parent stability explosions so powerful they left no neutron star or black hole behind, just an expanding cloud of pure hydrogen, helium, and the first traces of heavier elements. Some of those elements now drift before you: carbon, oxygen, nitrogen, the universe's first experiments with complexity. These atoms are the pioneers, forged in that brief window between the first star's deaths and the second generation's birth. They're extraordinarily rare here in the halo, perhaps only a few atoms per cubic meter. But their presence changes everything. You follow one particular oxygen atom as it journeys toward a denser region of the halo. Over billions of years, it's been incorporated into molecular clouds, then ejected by supernovae, then swept up in galactic mergers, a perpetual wanderer. Now it finds itself drawn toward a new star-forming region in the galactic disk, where it will become part of a rocky planet's crust. That planet, in some distant future, may host mountains that erode, sending this oxygen atom into a primordial ocean where it helps form the first organic molecules of life. The thought gives you pause. Every heavy element in your body, the oxygen you breathe, the phosphorus in your DNA, the iron in your blood, was created in stellar furnaces like these. The calcium in your bones was likely forged in the last violent moments of a dying star. You are, quite literally, the universe's way of remembering its own history. Back in the halo, you notice another population of stars, slightly younger, their spectra showing faint but definite metal lines. These are the second generation, born from gas enriched by those first supernovae. Their presence marks the transition from a simple universe to a complex one, from a cosmos that could only make hydrogen and helium to one that could craft carbon, oxygen, and all the building blocks of planets and life. Some of these second-generation stars are peculiar. A handful show extreme abundances of certain elements, carbon stars with atmospheres like soot, or stars with bizarrely high oxygen content. These oddities are chemical fossils, recording the specific nucleosynthesis patterns of their parent supernovae. Each is a Rosetta Stone for decoding the lives and deaths of stars that vanished before Earth formed. The most fascinating relics are the ultrametal poor stars, those with metal content less than 1/10,000th of the Sun's. These are the stars that formed from nearly pristine gas, contaminated by just one or two previous. Their element patterns reveal the individual nucleosynthetic signatures of those first massive stars, allowing astronomers to reconstruct properties like their masses and explosion mechanisms. You drift toward one such star, a faint blue straggler in the halo. Analysis reveals it's actually two stars, a binary system where the smaller companion has been siphoning material from its larger neighbor. The stolen material shows an astonishing pattern, enormous amounts of strontium and yttrium, but almost no iron. This peculiar signature matches predictions for neutron star mergers, the violent collisions that create the universe's heaviest elements. Here, preserved in this binary system, is evidence of one such cataclysm that occurred before our solar system formed. The halo story isn't just written in stars. Between them flow streams of gas, some nearly pristine, others enriched with heavier elements. These are the galaxy's circulatory system, remnants of ancient accretion events and long-ago outflows. Some streams contain stars moving in unison, the shredded remains of dwarf galaxies consumed long ago. Others are pure gas, perhaps falling into the Milky Way for the first time after spending billions of years in intergalactic space. One particularly dense cloud catches your attention. Its chemistry is bizarre, extreme abundances of elements like europium and gold, but very little oxygen or silicon. This is the fingerprint of a rare type of supernova, perhaps one that formed from the direct collapse of a first-generation star into a black hole. The cloud is currently falling toward the galactic disk, where its unusual chemistry will someday be incorporated into new stars and planets. As you survey this stellar graveyard, you realize the halo isn't just a repository of old stars. It's a living record of the galaxy's growth. Each stellar population, each chemical anomaly, each stream of gas tells part of the story. The Milky Way didn't form all at once, but through countless mergers and accretions over billions of years. The halo preserves this history like tree rings preserve the history of a forest growth. Your gaze drifts back to the ancient red giant. It pulses slowly, its outer layers beginning to drift away in a gentle stellar wind. In a few million years, it will shed its outer envelope entirely, forming a planetary nebula and leaving behind a cooling white dwarf. The expelled material, enriched slightly by the star's internal nuclear reactions, will mix with the interstellar medium, contributing its tiny increment to the galaxy's chemical evolution. This is how galaxies grow richer over time. Each stellar generation contributes its elements to the next. The first stars had only hydrogen and helium to work with. Their descendants inherited carbon, oxygen, and iron, Today's stars form from material enriched by countless ancestors. The universe is learning chemistry, one stellar lifetime at a time. And you, whether as observer or participant, are part of that story. Every atom in your body was forged in some ancient star's heart or death throes. The gold in your jewelry was likely born in a neutron star collision. The uranium in Earth's crust was created in a supernova's unimaginable fury. Even the hydrogen in your body's water is primordial. It's been part of the universe since the first few minutes after the Big Bang. The halo's oldest stars continue their slow dance, oblivious to the significance of their existence. They are both artifacts and architects, relics of the past and builders of the future. Their light, though faint, carries stories older than Earth itself. As you leave the halo's quiet relics behind, your attention is drawn to the galactic disk, where these ancient gifts of stardust have ignited a new revolution, one where gas and gravity conspire to build not just stars, but worlds. Eighth, a constellation of life? Could there be others, adrift in the glow? Planets spin in the Goldilocks zones of alien suns, and you imagine. The galactic disk spreads beneath you like a jeweler's display. Countless stars glittering against the velvet dark, each a potential sun to unknown worlds. You drift toward a middle-aged yellow star, its golden light familiar yet foreign. Around it orbits a family of planets, their dances choreographed by gravity over billions of years. One particular world catches your attention, a marble of blue and white hanging in the blackness, its atmosphere streaked with clouds, its surface glinting with liquid water. This planet orbits squarely within the star's habitable zone, where temperatures allow water to remain liquid. But location alone doesn't guarantee life. You examine its history. The planet formed from the debris of earlier stars, its iron core still molten from radioactive decay. A massive moon, born from a cataclysmic collision in its youth, stirs the oceans with tides. Volcanic activity cycles gases through the atmosphere, while plate tectonics recycle surface material over geologic timescales. All the ingredients are here, but are they mixing? The atmosphere tells a promising story. Spectroscopic analysis reveals oxygen, lots of it, alongside methane and water vapor. On Earth, this combination would scream life, since oxygen reacts so readily with other compounds that maintaining significant atmospheric levels requires constant replenishment. But false positives exist. Photochemical reactions or geological processes can sometimes mimic biosignatures. You look deeper. Faint but unmistakable, another signal appears in the data. Chlorophyll's distinctive red edge, the spectral signature of plants harvesting sunlight. Or something like plants. The biochemistry might differ, perhaps using different pigments or alternative molecular machinery, but the principle remains. Something on this world has learned to eat light. Night falls on the planet's surface as you draw closer. The darkened hemisphere sparkles with clusters of light, not the random scatter of wildfires, but organized patterns suggesting technology. Radio signals whisper upward, though whether they carry music, speech, or something unimaginable remains unclear. The civilization, if that's what it is, appears young, perhaps at a stage similar to Earth's early industrial age. You wonder, are they looking up too? From their vantage point, your merged galaxy would appear as a fuzzy patch in their night sky. Their astronomers might debate whether it's a distant cloud of gas or an island universe, like their own spiral home. Some might speculate about life existing out there, while others dismiss the idea as fantasy. A few might even be pointing crude radio telescopes in your direction, listening for signals they don't yet know how to interpret. The planet's biosphere proves astonishingly diverse. In its oceans, microbial mats build layered structures resembling Earth's earliest stromatolites. More complex organisms fill every niche, some with familiar bilateral symmetry, others with radial or fractal body plans never seen on your world. The land hosts towering photosynthetic structures that aren't quite plants. They're circulatory systems based on metallic compounds rather than organic fluids. Flying creatures glide between them, their wing structures suggesting multiple independent evolutionary origins of flight. Life here found different solutions to common problems. Instead of DNA, this world's organisms use a similar but distinct molecule for information storage, one with an extra strand in its helical structure, allowing more robust error correction during replication. Their cellular machinery incorporates silicon alongside carbon, enabling structures that would collapse under Earth's biochemistry. Some organisms even use quantum tunneling in their photosynthetic processes, achieving near-perfect energy transfer efficiency. But life isn't confined to this single world. As you survey the system, you find extremophiles everywhere, bacteria-like organisms thriving in the acidic clouds of the inner planet, methanogens swimming in the subsurface oceans of an icy moon, even radiation-resistant microbes clinging to asteroids. The raw materials of life, organic molecules, liquid solvents, energy sources, appear abundant throughout the cosmos. Given the right conditions and enough time, life seems almost inevitable. Your attention returns to the technological species. Their civilization shows both promise and peril. They've begun harnessing fossil fuels, altering their climate in ways they don't yet comprehend. Their first tentative steps into space, primitive rockets and orbiting satellites, suggest they'll soon face the Fermi paradox firsthand. If life is common, where is everybody? Perhaps they'll find answers in the cosmic ruins you've explored, the remnants of merged galaxies, the ashes of dead stars, the silent evidence of countless civilizations that rose and fell before them. The thought chills you. Intelligent life may be nature's most fragile experiment, a candle flame in the cosmic wind. Technological civilizations might routinely snuff themselves out through war or environmental collapse before achieving interstellar travel. Or perhaps they transcend biology entirely, transitioning to forms we wouldn't recognize as life. The most advanced civilizations could be all around us, their activities indistinguishable from natural phenomena. Yet hope persists. Elsewhere in the galaxy, you spot other promising systems, a red dwarf with tidally locked planets where life clings to the twilight zone, a binary system with organisms adapted to regular stellar flares. Even a rogue planet warmed by radioactive decay and geothermal vents, its entire biosphere existing in perpetual darkness beneath an ice shell. Life, it seems, will find a way wherever physics permits. You recall the cosmic timeline. The universe is 13.8 billion years old, but Earth's technological civilization has existed for mere microsecond on that scale. If intelligent life is common, there should have been ample time for earlier civilizations to arise, spread, and leave detectable traces. Their absence, the Great Silence, could mean many things. Maybe spacefaring civilizations are rarer than we think. Maybe they're deliberately avoiding contact. Or maybe we're simply not listening correctly. As dawn breaks over the alien world, you watch its inhabitants awaken to another day of questions and discoveries. Somewhere among them, a scientist peers into a microscope, an artist captures the sunrise, a child wonders what lies beyond the clouds. They don't know it yet, but they're part of a much larger story, one written in stardust and gravity, spanning billions of years. The universe has grown aware of itself here, as it has on your world. How many other eyes gaze upward from how many other worlds? How many civilizations have risen and fallen without ever knowing they weren't alone? The cosmos keeps its secrets well, but the evidence suggests we're part of something vast, ancient, and alive in ways we're only beginning to understand. As you pull away from this living world, its glow fading to a pale blue, you carry a new awareness. Every atom in your body was forged in stellar furnaces so that one day, the universe might look back on itself and wonder. Ninth, drifting back to dream. The screen fades to black, but the stars remain behind your eyelids. You surrender to the pull of sleep, cradled in the same forces that birthed galaxies, still drifting, still becoming. The cosmic journey has come full circle. The merged galaxy now spins silently below you, its spiral arms shimmering with starlight older than Earth itself. All the stories you've witnessed, from the first gravitational whispers to the rise of alien civilizations, exist now as memories woven into the fabric of your consciousness. The universe continues its endless dance, but your eyes grow heavy with celestial fatigue. You float in the interstellar medium, where the temperature hovers just above absolute zero. Here, the silence is so profound it hums. Each cubic centimeter contains perhaps a single hydrogen atom, a near-perfect vacuum by terrestrial standards, yet brimming with quantum potential. The cosmic microwave background radiation, that fading echo of creation, bathes you in its gentle 2.7 Kelvin glow. This is the universe's oldest light, stretched and cooled over 13.8 billion years, now serving as a nightlight for your cosmic slumber. Your body, composed of star-forged elements, recognizes this moment on some primal level. The calcium ions dancing across your neurons were born in supernovae. The iron in your blood was forged in stellar cores. Even the water molecules hydrating your cells contain hydrogen atoms that date back to the Big Bang. You are, in the most literal sense, the universe temporarily arranged into a form capable of contemplating itself. As you begin your drift towards sleep, the galaxy's rotation becomes your lullaby. Every 230 million years, the Milky Way completes a single turn, a cosmic hour hand marking time on scales incomprehensible to human biology. Yet your slowing heartbeat somehow synchronizes with this grand rhythm, your breath matching the pulse of variable stars in the distant halo. Memories of the journey flash like shooting stars across your mind's eye. The first proto-galaxies forming at the intersections of dark matter filaments, their gravity wells collecting primordial hydrogen like dew on a spider's web. Ancient population 3 stars, hundreds of times more massive than our Sun, blazing brilliant blue lives before exploding in parent stability supernovae that seeded the cosmos with its first heavy elements. The slow ballet of merging galaxies, their spiral arms stretching into tidal tails studded with newborn star clusters, while supermassive black holes circled each other in a deadly pot of dew at the core. That miraculous exoplanet with its silicon-carbon lifeforms whose photosynthetic structures littered like crystalline forests under a binary star system. The paradox hits you as sleep's event horizon approaches. Everything you've witnessed exists simultaneously in both the distant past and the eternal present. The light from those merging galaxies took billions of years to reach your eyes, making you a time traveler as much as a space traveler. The universe's history isn't locked away in books, it's written in light years and spectral lines, waiting to be read by anyone who knows how to look. Your body begins dissolving into the cosmic background, not literally, but perceptually. The boundaries between self and space soften as sleep approaches. The same quantum fluctuations that seeded galaxy formation now spark random neural firings, dreams waiting to be born. The dark matter halo cradling the Milky Way becomes your blanket, its gravitational embrace gentle but inescapable. A final realization dawns. You've been given a perspective no earthbound astronomer could ever achieve. From your vantage point outside the galaxy, you've seen time as a dimension to move through, not just a river carrying you forward. The past isn't gone. It's simply over there. Its light still traveling. The future isn't unformed. It's already written in the collapse of protostar clouds and the gravitational interactions of dwarf galaxies. As consciousness fades, the cosmic web becomes your neural network, each filament of galaxies mirroring the synapses in your sleeping brain. The universe dreaming itself into existence. The great attractors pulling galaxies towards some unknown destiny become the emotional currents shaping your dreams. Superclusters form and dissolve like thoughts in the mind of God. The last thing you perceive before sleep takes you is a single, impossible idea that this entire journey may itself be the dream of some greater consciousness. That universes might be born in the minds of sleeping giants. That existence could be an infinite regression of nested realities, each with its own physics and constants. But now, none of that matters. The cosmic story will continue without your witness. Stars will be born, live, and die. Civilizations will rise and fall. The universe will expand until most galaxies disappear beyond an unreachable horizon. And you? You'll sleep, cradled in the arms of the same forces that shaped quasars and nebulae, your breath synchronized with the slow heartbeat of an evolving cosmos. Tomorrow, whether in hours or eons, you may wake to new wonders. Perhaps to witness the Milky Way Andromeda collision, or to see red dwarf stars entering their trillion-year reign as the universe's primary light sources, or to find that some civilization has learned to harness the energy of entire galaxies. But for now, there is only this perfect moment at the boundary of awareness, where the distinction between observer and observed blurs into quantum uncertainty, where the cosmic and the personal become one, where the great story of everything pauses just long enough for you to find rest within it. The universe began in a dream, and to dreams it now returns. Final lines. As consciousness fades to black, the stars don't disappear. They simply become the twinkling of a billion neural connections, the universe folding inward to dream new worlds behind your sleeping eyelids. Good night, little cosmos.
And now, as a start, continue their silent dance. May your mind rest with the rhythm of the universe. Galaxies will keep turning, stars will keep shining, and you can simply sleep. Fellow traveler of the cosmos, good night.